So this is a session on OpenCAPI memory interface. There was just one previously. Your slides were a little better than mine, but talk a little bit about what we're doing here. I conglomerated slides from several different sources, so hopefully kind of present a reasonably consistent view of what we're doing, but just trying to give a basic overview of that. So I stole this slide. I think everybody needs to acknowledge who they stole their slides from. This was from Brian. Allison, thank you. So the industry landscape here is essentially we have, and this is I think the next, I have a couple slides that all kind of work around this same topic here, but we have heterogeneous computing, which means we need to attach network offload, GPUs, other types of accelerators close to the processor. We have new emerging memory types, right? So before, pretty much DRAM was all that was on the horizon forever, and now we have a variety of new technologies sort of on various horizons. We'll see which ones win first. We've got Ken with his hybrid one, which I actually like quite a bit. There's raw phase change memory devices, and there's actually a pretty long list of things that we're looking at internally, different DRAM targeting points, different types of somebody was presenting a few weeks ago at Hot Chips on carbon nanotube memory, right? Which was actually a good presentation. We should all be buying it by now, right? It was I don't know who was at that talk, but he basically said, I made a DDR4 compliant device that's like cheaper, faster, better. But there's a whole bunch of new memory technologies. Some are more vaporware than others, but we have to be able to quickly adapt to those. And that's a big part of what OpenCAPI memory is the ability to plug in different types of memory into your box. So let's look at this one. This I think I took from McCready, from Brad. So here we have, and I like this in some regards, but in the other sides, there's things I miss. So yesterday's plumbing is tomorrow's differentiation. Definitely think that's true. It used to just be DDR memory. No real way to differentiate, though we did. Historically, IBM has differentiated on memory with our buffered memory solutions. If you look at what we've been doing, we've been doing buffered memory for a long time to give us capacity and reliability out of really what is a commodity DRAM chip that goes across a broad range of computers. And so if you're trying to build a high scalability enterprise server, a mainframe, whatnot, and all you have to work with is these commodity DRAM chips, you kind of got to do something special to make them resilient enough for your usage. So we've been doing that forever, and that's part of what we're providing to the overall ecosystem here, is taking our experience in that space and conveying that into an open standard, which is what the OpenCAPI thing is. The other side of things is I/O. PCIe I actually think is a pretty good standard compared to even previous PCIe. The switches have pretty good, the high frequency SerDes, right? They're actually pretty good interfaces for connectivity, especially of lower latency or higher latency devices. If your device is in the many, 100 microseconds, 10 microseconds, PCIe is reasonably good at transferring to those. But PCIe is really centric around, DMA transfers. There's quite a bit of latency in the path, and it's not really designed to be tightly coupled to the device. So how we like to differentiate is doing things better than PCIe. What we have today is NVIDIA NVLink, which makes our AC922 computer, our Summit systems, very differentiated, but this is a proprietary standard. So, right, NVLink's proprietary. A big part of what OpenCAPI in general is building an open interface on that, right? So, but yesterday's plumbing, the thing I somewhat don't like about this is it's sort of, cores and caches. Those aren't a commodity device yet. A big part of my job at IBM is designing the cores and caches, and so we're still continuing to differentiate and build better cores and caches, but it is becoming more challenging with the whole Moore's Law thing on the, happening. So, anyway, let's keep going. So we're back to one of Brian's slides. So when we look at what OpenCAPI has to do, it has to manage these new memory, storage, kind of hybrid devices. Is it a storage device? Is it a memory device? We also have to be able to deal with network offload. That's what the last session in this room was about. And so we've got to do all these different things, right? There's nothing today that really lets us do that, especially in a hybrid way, right? If it's a sort of a memory and a storage device, it might need to do things that memory, it may need to master commands. Maybe just to go tell the processor, hey, I've run out of decompressed memory, or I need some kind of maintenance on my structures. You can't really do that very efficiently across a DDR interface today. We also have, deep learning. Obviously, there's the computational demands have grown beyond what they used to be as well. Historically, when we made servers, they all ran, much of them ran OLTP, right, as a big database server. Now we've got people are actually deploying machine learning, deep learning into actual ecosystems. So we got a bunch of different things we need to build into our bus. We need to be coherent. We need to have that for the acceleration, tightly coupled accelerators, tightly coupled network offload. But really the one we're talking here about is we need to be able to take different memory technologies and plug those into our processor. Right? So how do we do this? We got to have open ecosystem. You couldn't do this with PCIe, right? So if we're looking at where we're at today, we've got DDR. DDR is tied to one memory technology, deterministic latency, pretty much zero flexibility. And then you've got PCIe, which has much too high of latency and no way to build coherence across it. And so we're really merging those two things together into one performant solution. So that's our, that's how kind of OpenCAPI was born, right? Is to take something new and then build it better. Now that said, a big part of what we're doing, let's talk a little bit about what's not in OpenCAPI. Part of the reason PCIe has higher latency is it's very strict packets. So it has packets. The packets, you can go through PCI switches. Everything's sort of self-contained within one CRC code. OpenCAPI, based around our experience with CAPI and the DMI memory interface, has a very naked interface. The complexity of it, it's very tightly coupled to the processor, which in some senses means it doesn't encapsulate things as well as PCIe or Gen Z does. So what we have is essentially a way to put logic on an accelerator or a memory and be able to get back and forth to the processor with very small packets and very specifically formatted packets. I don't talk about this in the session here, but the packets are strictly aligned to a specific cycle ratio in the processor. So when we send a 64-byte chunk of data between the processor and the device, we know that that will land on a specific clock boundary on the attached device. Because of that, that means we can start to interpret the data very quickly, right? So everything's very specific packet formats where you're basically taking logic from the CPU and sticking it right in the middle as if it was in the same pipeline as the processor in the accelerator or the memory device. So because of that, they're very tightly coupled. It's not very amenable to switch topologies because you're not, it's really designed to talk to one device as if it was on the processor, not to go talk to a network. So you got to keep that in mind with these devices. It's really putting accelerators on the CPU, but in a sort of a one-to-one way. But that's the target here. And we want to do the same thing with, be it memory or accelerators. We both want them to be as if they were on the processor die. So here's a chart. This one did Bruce do this or did Brian do this? Brian? Thanks. Everybody raise your hand if it's your chart. So here it shows the continuum, right? So the OpenCAPI interface, we want to be able to have, you plug in one of these, which is memory, right? So just DDR buffered memory goes into a slot. Maybe instead of memory, you want to plug in something that has non-deterministic latency, right? This one, the latency goes out here. DDR is pretty deterministic. It's pretty short. But what if you want to go to something that's SCM that may have really long write latencies? Another thing to talk about, especially relative to DDR, is writes on this interface are explicitly acknowledged. So when you do a write to DDR, you just shove the bits across and then you assume it completed, which is a bit of a problem when you're looking at power failure transitions. So if your box power goes out and you're in the middle of doing a DDR write, did it complete or did it not complete, right? You don't really know. So what we can do here with OpenCAPI is the controller here can say, oh, this write completed. That can then let the fence and the CPU say, yes, software, the write did definitely complete. And so we can do things, if we can start to get to SCM and other types of devices, we can buffer up writes. Maybe they are not yet persistent, but they've been acknowledged by the controller, and we can put some amount of capacitance on the controller, or maybe it's in its own power domain, right? So this is a connector, or it could be a cable. So the memory device here could actually be in some other appliance sitting next to the processor. that you're doing loads and stores to, right? So that other box has its own power domain, and so as soon as the write makes it across, the other box can acknowledge it, the processor could fail, and we've had a very clean handoff of the write across the interface. So that's like a storage class memory. Other things we could do is, this is showing it as, sort of cascaded OpenCAPI interfaces, but really the device here that's probably more relevant is possibly a device that has both DDR in it and other types of memory. And this is really what Ken's, would you say this is close enough match to what Ken's thing was doing, right? So we got DDR, which is frequently accessed, and then you have some other larger pool of memory that you use as sort of a second level tiered memory solution. And so the goal here in these cases is maybe SCM, but maybe it's really just cheap memory, right? DRAM's quite expensive. Some of your data needs to be in DRAM because it's frequently accessed, but some of your data is pretty cold. But that said, you still need to be able to load to it without having, you can't do a load to a spinning disk, for example, or really even an NVMe, unless you can make it infrequent, right? So we got to have reasonable latency here, but not hang the processor. And so that's kind of what we're doing with these two scenarios here, is mixing those two. So that brings us into this form factor discussion. So we have a variety of form factors. These plug into a connector that we actually co-developed through JEDEC. We didn't start with this connector, right? We started with more of a DDR-like looking connector, and we had a little bit of arm twisting to get to this connector. If you went to like a Gen Z presentation, you will see that this is the exact same connector as Gen Z. So we are working with other companies. We are moving our standard. That's probably a good thing to state, is this isn't just IBM saying, okay, world, here is OpenCAPI. It's an open standard, but we dictated it. We actually moved our standard quite a bit to match what other organizations were trying to do. And so Gen Z, which is a switched memory fabric, not as low latency as OpenCAPI, but it does use the same differential signaling and the same connector. And so somebody could build a system that you could plug a Gen Z device in, or you can plug an OpenCAPI device in. And that connector this is showing a DIMM, like just to be a DIMM form factor, but there could be a cable that goes on here, and that cable could run out to an I/O drawer. Or you could put your SCM memory directly on in the slot itself. But this gives us composable systems, right? We could build high bandwidth, low capacity for HPC type systems. For something like an SAP HANA, we could do SCM to give it lots of capacity and a higher form factor. The other nice thing, I'll mention that memory cards today are pretty short, which works in a 1U server, but if you're in a 2U or a 4U server, you'd really like to just keep going up, right? So that's how we can get to high volume capacities of memory. Bigger server, same motherboard, but taller DIMM capability. Okay. So lots of, and this is also, you'll see this is sort of our higher reliability DIMM. It has redundant voltage regulators on it, so we can still build enterprise class memory on the same interface here. It's just a question of, do you put big or small? So let's talk a little bit about how we've taken, next slides, next little bit here is, what do we have today in Power 9? How does it work well? How does it not work well? And how does that transition into what OpenCAPI is today? Memory in particular. So today we have on our memory subsystem in Power 9, we have this is our industry standard cost density optimized solution. The only thing that was available when we started Power 9 was DDR memory. We hadn't built OpenCAPI memory yet. So we needed a dense solution. Why do we need a dense solution, a low-cost solution? The buffered memory solution we had, which is great, is this Centaur memory buffer. The Centaur memory buffer is a pretty big chip. This has a 128 megabytes of EDRAM cache on it. Each of these buffer chips has 4 DDR ports. We have 32 ports of DDR all funnel into one processor chip, right? This is compared with, Intel's at 6, we're at 8 here. We've got obscene amounts of DDR ports here, right? Obscene amounts of DDR ports, though, means big DIMM cards that just simply can't fit in a 1U box with much ease. I mean, we did put these, you see in Power 8 OpenPOWER systems, they all had these buffer chips, but the buffer chips ended up going on the motherboards. So when you see a standard DIMM plugged into a Power 8 box, you had to go off and buy one of these Centaur chips, and they're somewhat expensive. They take up space on the motherboard. So if you're trying to do a dense server in the same form factor as x86, you got to stick a bunch of these chips down on the motherboard. You got to pay for them. It's really a cost problem. That said, this has this agnostic interface that I was just saying how great it is, right? It also has very high bandwidth interfaces. So there's a lot of really good things about this. The problem really was it being open, and the particular buffer we built was optimized around large enterprise servers, not around dense servers. But lots of good stuff here, especially the agnostic interface, and we've been doing work here with this, right? So there's a recent micro paper that I guess got best paper with a FPGA-based solution here where they're evaluating different latencies. So lots of good work is happening in this form factor, but it's not really a shippable case, right? It's too big, too expensive. I guess that card actually sticks out of the top of a 4U box, right? So it's a test vehicle, not a production vehicle. So I think this has come up a few times, but this is our two Power 9 chips with the two different memory subsystems. I'll try and inject some humor here. So Power 9 has a family of processors, and right, it's a family. Why do we have a family of processors? It's because we're trying to target different spaces, right? We're trying to do well in dense supercomputers. That requires a different chip than the enterprise class system. So at the start of a project, we plan out our family, right? So we planned our family to have this type of memory and this type of memory. And then we said, okay, here's our children. So how do we do that, though? We take all the other stuff here, all this complicated, difficult to design stuff in the middle, we keep it the same, and then we change out components. So in this case, the components we change out are, this is 4 channels of DDR-Phi, and this is 4 channels of DDR schedulers and controllers. And then you have another 4 channels of DDR-Phi down here. This takes up quite a bit of perimeter area, though, right? We've taken up nearly half of our chip perimeter, and this is a very large chip, just to drive 8 channels of DDR. So you can see if we wanted to get to more channels of DDR, it's really not possible, right? We could go to 16 channels of DDR if we had nothing else coming off of our chip other than a little bit of PCIe. This is really highlighting how sort of end-of-the-line DDR-Phis are. They're simply very large. This is the Centaur DMI-based Power 9 chip. This is 4 channels of DMI, right? It's smaller. It's about half the size of that, right? So per wire, this is running at 9.6 gig, right? This is running at 2666. That said, this isn't even as fast as we can go. If you look at our OpenCAPI and VLink, these are running at 25 gig, right? But the key point here is that this is much smaller than DDR-Phi. So what did that let us do in the Power 9 big chip family? Since we didn't have to put as much space on for the memory interface, we have twice as many 25 gig wires for SMP and OpenCAPI. We also were able to fill up this whole edge of the chip with our other SMP Connect. It's kind of unfortunate. You'll see there's some missing space here. This is exactly 3 interfaces. We had to cut it down to 2 interfaces because the DDR-Phi went over the edge there. But you can see here, so now we have, I don't have a picture for this, but we have an unplanned family member. This is where things get a little funny, right? So you can't always plan your family. Sometimes things happen and you end up with another child. Don't tell your wife. Same, yeah. It's the same mother, though. Yeah, same parents. And we had this with Power 8. It kind of works well, because in Power 8, we built 2 chips, and then our unplanned child was in VLink. And we love it just like our other children, right? The thing you get to do, though, is whenever you have a new family, you get to remember what happened in your last family, and you plan better. So in Power 9, NVLink is in all the chips, right? We knew about it at the start. We always have NVLink. So the new unplanned child is OpenCAPI memory and improving OpenCAPI in general. OpenCAPI was a relatively late addition to Power 9. We were able to get it in, but not everything we wanted to. And so we get the rest of it, which is OpenCAPI 4.0, but also OpenCAPI memory. So what does Power 9 derivative chip look like? I don't need a new picture because just whatever was here with our 9.6 gig differential is now 25 gig differential. In the memory controller that talked to Centaur, we swapped that one out and we put in a memory controller that talks to OpenCAPI memory. So Power 9, same chip, quickly deploying OpenCAPI memory before a new process technology comes out. So it pretty much looks identical, except for here you've got 25 gig signaling. Talk a little bit about different versions of OpenCAPI. Here's our Power 9 that has our version 3.0 of OpenCAPI. You know, the first generation of OpenCAPI is 3.0. That makes sense. Well, because we had 1 and 2, right? We can't. Yeah. Anyway, 3 is better than 1, right? So, and this does 25 gig signaling. You will notice here, though, we don't have caching capability on 3.0. It's strictly a DMA agent. We didn't have time in the schedule because we did add OpenCAPI somewhat late in the design process to Power 9. So you'll see when we go to the follow-on Power 9, our next child that we'll love, we have the OpenCAPI 3.1, which is the memory interface we're talking about. And we also extended the 4.0 OpenCAPI, which contains caching capability. Now, there are some improvements, and this isn't the session on this, but the caching that was done in CAPI 1 and 2.0, we learned quite a bit from that. There's a pretty big chunk of logic on the FPGA called the PSL. We moved nearly all of that logic onto the processor chip for this next version. And so if you look at the way we're doing caching in 4.0, it was definitely learning from the way we did it in these previous generations to enable a more efficient caching solution. So yeah, here we have, but it's all 25 gig, right? We got 25 gig signaling, essentially we'll have 16 connectors for memory. So here's some pictures. Obviously, this is a completed picture of Centaur, just to give you a perspective on what we're doing different. So Centaur was big old chip. It had 4 DDR interfaces. They're quite large on the buffer chip, just like they are on the processor. And then here is our differential signaling link. This is a 16 megabyte cache. We put 8 of them in the box. That's how we get 128 megs. And here's our scheduler. The scheduler and the management for the cache itself. So our new buffer chip, these are not to scale. This one's similar. It's smaller than this, but this is how big I put it on the chart to make the text work. This is our new buffer chip. You can see that this is the OMI, and this is the DDR PHY, and here's the scheduler. It's a very short distance from here to here, and so the latency through this buffer chip is quite low. Our target is on the order of 5 nanoseconds. We might be a little higher than that, but the amount of time you spend in the buffer chip is very small compared to here where you had to go across the scheduler and out to these bigger DDR PHYs. I don't have a picture of the Centaur DIMM, but the distance from the Centaur to the memory devices is also longer. When you see the OMI DIMM in a second, you'll see it's very small, and we can run these at very high frequency. I think that's coming up in a few slides. But yeah, so this is what our buffer looks like. And this is the first one. We really like more buffers out in the world. And that's where I think a lot of the people in the community come in here. We're building one buffer straight away, which supports DDR4 memory. But we'd actually like to be able to support smaller memory capacities at high bandwidth, tiered memory, right? There's a lot of different memory interfaces, memory devices possible. Just to do a quick roadmap picture here, what we got is here is our Power 9 family. This is the 2 Power 9s we have today, our first ones, and then this is our OpenCAPI enabled one. But you'll see here on the memory interface, we have 350 gigabytes of sustained bandwidth into a socket. That's obscenely higher than anything else you'll be able to get. How do we get there? We were able to connect 16 channels of DDR memory, but we're also able to run the memory at higher frequency because it's a very short net from the DDR controller to the DDR device. So we're talking 3200 DDR4, 16 channels of that. So very much a high-performance memory subsystem. Next on the horizon is Power 10. Power 10, we have a whole new chip, right? It's a new process technology, a whole new chip. But that said, it will have the similar types of OpenCAPI and memory interfaces we have in this new Power 9. We essentially didn't want to wait till Power 10 came out to deliver this new technology, and that's why we put it into a Power 9-based solution. But same basic core design, but essentially whole new memory subsystem, and let's call it 2020. Thought I had one more slide in here. Anyway, I was going to, maybe I already blew through it real quick. Let's look, yeah. Yeah, let's go back to this one real quick just because I wanted to talk about that. This is our little tiny buffer chip, right? And so we're able to run this very short interface at 3200 quite easily. And when we get to DDR5, when people are trying to run extremely high frequency DDRs, we'll be able to do that, right? So compare driving a signal from here to here, right? Or I guess we'll talk about the longest one just to be fair, or even from up here to large, the higher distances. But that said, the high bandwidth solutions are probably a little dim anyway. So imagine trying to drive high frequency signals from there to there versus from a processor chip through the processor package, through the motherboard, through a DIMM connector, and up across the motherboard to the buffer chip. You would never go directly from the processor all the way to the data device, I guess, as DDR5 frequencies anyway. So you got to have some kind of buffer on the DIMM. You might as well make that high frequency SerDes that run at 25, 32 gig instead of something that's running down in the low 3, 2, 4, 5 gigs. So definitely the right way to do memory devices, and it lets us take that commodity DDR device and scale it to much higher bandwidths than you could if you drove it really all the way from the CPU chip. So I think that's all I have. Yep.